has an induced symplectic structure. And if you want me to later on in discussions, I can say exactly how the symplectic structure is derived from the action. It's easier to say very quickly what the inverse of this is and give the Poisson structure. So a symplectic structure on P means a Poisson structure on functions. And the structure is such that the Poisson bracket between a field and the variation of the action with respect to the time derivative of that field is 1. By any field. And again, saying time derivative only makes sense because I set up the problem so that we have a distinguished time direction. Then one uses some method to quantize this phase space with its symplectic structure. Here that's going to be geometric quantization.
Could I just add about this point briefly? We can discuss this in detail later, but I just wanted to register the question. I've always been somewhat confused by this because, of course, one describes this often in terms of a symplectic structure. I like that description fine. But if you look at this as the critical point of a function, it also has a Lagrangian submanifold structure of a cotangent and
yes.
Lagrangian intersection structure.
Yes.
Which would give you the -150 symplectic structure.
Yes.
So what's the relation between these two?
So I have been told this many times,
right.
And is something I would love to understand.
Right.
And there are people like Phil who would tell you the answer immediately.
Okay.
Unfortunately, not here.
Actually, he didn't tell me the answer to this immediately, I guess.
But yeah, so that's right. So any critical locus has a shifted symplectic structure. I think combining that and some ideas from the BV formalism leads you to this standard unshifted
So you think these
structure.
are related? Yeah.
But yes.
Phil, for example, thought that they were unrelated.
But you should take that with a grain of salt. I'm not sure.
Okay. But he wasn't sure.
So step 3, quantize. In the symplectic space, for example, so it's known how to do this in certain cases. For example, if P is scalar, quantization produces the Hilbert space as holomorphic sections of a line bundle whose first Chern class this is a complex line bundle whose first Chern class is the Kähler form. Great. Then functions on phase space get promoted to differential operators. On on the Hilbert space, which is how one gets a representation of the operator algebra. And finally, there is a procedure to pull the Hamiltonian out of this. I will just write the basic result in the case that, so if the action is the integral of a local density of some Lagrangian, then the Hamiltonian classically looks like an integral over sigma of phi dot ds d phi dot minus L. So these were the conjugate variables that entered the Poisson structure. There's a sum over all fields. There are better ways of saying this. I just wanted to write a formula down. So there is a way to extract classically the Hamiltonian. Another way to say it is that it's the Noether charge for a conserved time translation, which is what this formula gives you, and then one plugs it through the quantization machinery to find the quantum operator. Notice that the Hamiltonian is not a local. It's not a local operator. It's something integrated over a surface, which it had better be if it's going to implement time translation.
So in your previous terminology, is this also an interface operator?
Yeah, I mean it is. I don't think anyone used to think of it that way, but it certainly is. It has to be an interface in order to actually act everywhere on the Hilbert space. Okay.
When you write S as an integral of L, what are you integrating over there?
Sorry?
When you write S as an integral of L.
Oh, sorry. That's over M. Over M. And the games where the dimension of the space I'm integrating over changes makes sense precisely because I have a distinguished time direction, and there's a vector field in that direction that's being contracted. Okay. That's it for general structure. I'd like to say some things about quantum mechanics. So by quantum mechanics, I mean one-dimensional quantum field theory. In that case, my manifold M is going to be R or S1, or possibly an integral with boundaries. And so the fields are sections of some bundle over R or S1. I can think of a section of a Y bundle over M as locally is just a map from M to Y. That's going to describe the path of a particle moving in Y. And that's why 1D quantum field theory looks like quantum mechanics, because its fields are lines of particles. Y is often called the target space of the quantum mechanics. We're going to consider a slightly simplified, some might say unphysical, quantum mechanics theory.
I'm sorry, I'm a little
that's-
confused about the notation. So is E over M the bundle or Y over M the bundle?
Sorry, Y is the fiber.
Y is the fiber.
Right. So a section looks like a map from the base into the fiber.
Okay.
And so it looks like an embedding of, say, it's a trivial Y bundle over R. A section of the bundle just looks like a map from R to Y, which is the path of the particle moving in Y. So for topological quantum mechanics, take Y symplectic. In fact, in all the examples, so that quantization is easy, actually, I will assume that Y is Kähler. Then, right. Again, fields look like maps from M to Y locally. And given a symplectic form on Y, I'll construct the action. Well, there's a simple local formula, and there's a nicer global formula. I'll give you the local one first. Symplectic form is closed, so locally it's exact. So omega is d theta locally. And then the action of the theory. So let me call these maps phi.
Sorry, to interrupt a second. When you take Y to be symplectic, from the other viewpoint, are you viewing Y as the phase space of the particle?
So it will end up being the phase space, but that's not a priori obvious. So the reason I want Y to be symplectic is so that I can write down a particularly nice first order action.
So a priori, when you think of a path in Y, then you're letting the momentum and the position be just independent of each other.
Yes. So the action is going to be the integral over M of the pullback of theta. Does that make sense? So phi was my map from M to Y, and using theta, I get a one form on M, which is R over S1. Just integrate that. So, example. Let me take Y to be the cotangent bundle of R. With coordinates x, p. And a symplectic form dp dx. So I can take theta with some ambiguity to be p dx. Then fields If my manifold M is just the real line, then fields are some functions, P of T and X of T. And the action is an integral along the line of P of T x dot of T. The equations of motion set, well, one of them is easy to see. So ds dp just sets x dot to 0. ds dx, to evaluate that, we need to integrate by parts first and move the derivative onto p. So that'll set p dot to 0. So classically, this is a theory where nothing is happening. We have a particle that starts at some values of x and p, and it doesn't move, which is good because I want a topological theory. So you can also check that that the Hamiltonian is 0, classical Hamiltonian. So it's the Hamiltonian. It's ds. It's, well, you can check. That it vanishes, which is consistent with the fact that nothing is moving. To find the Hilbert space, we'll first compute the phase space at a time t. So this is solutions to the equations of motion on a small interval. But since the equations of motion are first order and nothing is moving, this is just values of p and x at that fixed time. And so the phase space ends up being a copy of y itself. Answers that, the original question.
And sigma is just a point.
Mm-hmm.
Sigma is just a point. You wrote
Sigma is just a point.
So
Yes.
yes. A point.
No. So the phase space is y itself. In this case, because the action is first order in derivatives, and the equations of motion are first order in derivatives. So in general, there would be extra derivatives of x and p that appear there. Great. So what does quantization give? The Hilbert space can be described as square integrable functions of x or of p. Where the two representations are related by Fourier transform, and then x and p as functions on phase space get promoted to operators, to differential operators in the top representation. So if we take L2 functions of x, then they become x and ddx. Right. So it's sort of the standard quantum mechanics story, but in a first order formalism. So the standard quantum mechanics story doesn't involve p, it just involves x. And the action looks like the integral of x dot squared, which is second order in derivatives. One ends up with the same description here. Except the equations of motion are a little bit different and the Hamiltonian is not zero. Okay. One last comment on this trivial theory. One can check explicitly that time evolution is trivial at the quantum level.
Oh, sorry, if you had that action EDT of x dot square, would you take y to be r or t star r?
I would take y to be r. So the original y does not need to be symplectic. This is a special structure that I'm imposing to simplify it. But yeah, so the phase space would be t star r, and the original y would just be r. So let's check that time evolution is trivial. What if we do a path integral over field configurations such that x is sitting at x0 at time 0 and sitting at x1 at time 1. So this is the time evolution path integral.
You don't give any boundary condition on the p?
No. So the boundary conditions should always be Lagrangian in phase space. Otherwise, the system gets over-constrained. And it's, again, a consequence of this thing being first order. That I can constrain x, but it's not actually consistent to constrain p. And in terms of the Hilbert space, its functions, its probability distributions on x. And so this is a delta function probability distribution on x.
Can I ask you a question about that Hilbert space? What you wrote down earlier was the Hilbert space was supposed to be a holomorphic section of a bundle element.
Yes. So I cheated. I did not do that here. One could do that here. So I could go to complex coordinates and work with a line bundle over C.
What's the general formulation of cheat?
I can cheat here because the space is linear, and
so if you didn't cheat, you'd say holomorphic sections of what bundle?
I want a bundle on C.
Yeah.
Whose curvature is the symplectic form.
Right.
It's a trivial bundle.
Yes.
The only place where the curvature is going to show up is in the Hermitian inner product on the Hilbert space, which I have not talked about. And then I would find that the Hilbert space consists, since it's a trivial bundle, I just get holomorphic functions. But with some care about analyticity, holomorphic functions on C are very close to, well, analytic functions on the real line.
Yeah.
these are L2 holomorphic functions with respect to this Gaussian measure.
Well, yes, and that's actually the way to say it. But and the measure is the measure has, as you said, a Gaussian factor in it, coming from the curvature.
Why do you not do? Why don't people like that? Why did you do the L2 functions on x?
Because when one starts out in physics, one does not know about complex line bundles. I was trying to connect to intuition that people in the audience might have had about quantum mechanics with particles moving in a real direction.
Yeah, some of us are just so dumb. We don't have that.
So if you don't have that intuition, ignore that completely and work with the complex. Yeah.
So the physicists talk about Hart densities as spaces of Hart densities of different spaces.
Yes.
So as a,
Right, because you need to be able to define probabilities. But I don't think that level of sophistication is going to come up.
I'm still confused a bit about the boundary condition. If I were just naively setting up a path integral for your edge space, your y equals t star r, right?
Yeah.
Then I give boundary, then a path starts at y and ends at y.
So I agree. It's not the right thing to do when the action is first order. I think that naive picture does not work all the time. And the correct notion of a boundary condition is a Lagrangian in phase space.
I see. And because the phase states ended up being y itself, this is somehow what you're doing.
That's right. So if you had the usual story with the second order action,
Right.
y would be the real line. The phase space would be t star of the real line,
That's right.
and a Lagrangian in phase space would be would give you a point on the real line,
That's
and then
right.
your intuition would be correct.
That's right. Yeah, I see. I think I see what you're saying.